Every atom in your body has been doing something unusual since the moment the universe began. Not just existing, not just moving, computing, processing information according to rules so precise, so consistent, and so deeply woven into the fabric of reality that some of the most serious physicists alive today believe there is no distinction between the universe and the computation it performs. Not a simulation, not a metaphor, the actual, literal proposal that the universe is a quantum computer and has been running since the first instant 13.8 billion years ago. This is not a fringe idea. It comes from the intersection of quantum mechanics, information theory, thermodynamics, and cosmology. It is supported by real evidence, real calculations, and real experiments. And if it is correct, then everything you think you know about what exists is incomplete. Not wrong, but incomplete. Because the most fundamental layer of reality is not matter, not energy, not space, not time. It is information. That word carries a lot of weight. So let us be precise about what physicists actually mean when they use it. In everyday life, information is something you read, something stored on a hard drive, something transmitted in a message. But in physics, information is not a metaphor. It is a measurable quantity. It has units. It obeys laws. And crucially, it cannot be destroyed. This is not a belief. It is a theorem derived from the foundations of quantum mechanics, and it is called the principle of unitarity. When a particle changes its state, when a quantum system evolves, information is conserved. It can be scrambled, redistributed, made practically inaccessible, but it cannot vanish. That rule is as fundamental as conservation of energy. And once you accept it, something remarkable follows. Every event in the universe, every collision, every decay, every interaction is not just a physical event. It is an act of information processing. John Wheeler understood this more clearly than almost anyone. Wheeler was one of the most influential physicists of the 20th century. He worked closely with both Einstein and Bohr, helped develop the modern theory of nuclear fission, and coined terms like black hole and wormhole. Toward the end of his career, he became increasingly convinced of something that sounds almost too simple to take seriously. He called it from bit. What Wheeler meant was precise. Every particle, every field, every force in the universe ultimately derives its existence from binary choices. From yes or no answers to physical questions, from bits. Not bits stored somewhere on some cosmic hard drive, but bits that are the substance of reality itself. In Wheeler's view, asking a question of the universe, performing a measurement, observing a quantum event, is not passive. It is participatory. It forces a definite outcome from a range of possibilities. And that act of forcing, of collapsing a probability into a fact, is the fundamental act of the universe. It is the universe computing itself into existence one bit at a time. This might sound abstract. So let us ground it in something physical. Consider an electron. In quantum mechanics, an electron does not have a definite position until you measure it. Before measurement, it exists in a superposition of possible locations, a spread of probability across space. When you interact with it, when light bounces off it, or an electric field nudges it, the electron is forced to resolve its ambiguity. It picks a state. It registers one outcome out of many possibilities. That resolution, that forced choice, is information being processed. It happens trillions of times per second, in every cubic centimeter of space in the observable universe. Scale that up. A single grain of sand contains roughly 10 to the power of 22 atoms, that is 10,000 billion atoms. Each of those atoms contains electrons, protons, and neutrons, each existing in quantum states that interact, evolve, and resolve. The information being processed in that grain of sand every second dwarfs anything humanity has ever built. And that grain of sand is not doing anything special. It is doing what everything does. It is participating in the computation. Now consider that the observable universe contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star burns through matter via nuclear reactions that are fundamentally quantum mechanical. And the space between them, which appears empty but is not, seethes with quantum field fluctuations, virtual particle pairs, and entangled states stretching across distances we have no intuitive framework to imagine. The total amount of computation happening in the universe at every moment is beyond any number that has practical meaning. And it has been happening continuously for 13.8 billion years. The physicist Seth Lloyd estimated the total number of operations the observable universe has performed since the Big Bang. His calculation, published in 2002, arrived at a figure of approximately 10 to the power of 120 logical operations. That is a 1 followed by 120 zeros. For comparison, the most powerful supercomputers ever built perform around 10 to the power of 18 operations per second. That is 1 billion operations per second. Lloyd's figure for the universe is not just larger, it is incomprehensibly larger. And it suggests that if the universe is a computer, it is by an enormous margin the most powerful one we know of. But the really important question is not how much computation is happening. It is what kind. Because there is a specific difference between classical computation and quantum computation, and that difference turns out to be crucial for understanding why the universe works the way it does. A classical computer, the kind that runs every phone, laptop, and server farm on Earth, processes information using bits. Each bit is either 0 or 1, always. There is no ambiguity. When you run a classical program, it follows a single path through the logic, evaluating one possibility at a time and arriving at a definitive output. Classical computers are extraordinary machines, but they are fundamentally sequential in a way that becomes a bottleneck for certain kinds of problems. A quantum computer works differently. Instead of bits, it uses quantum bits, called qubits. And a qubit does not have to be 0 or 1. It can be both at once. This is not a trick of language. It is a real physical state called superposition. A qubit in superposition has a certain probability of being measured as 0 and a certain probability of being measured as 1. And until that measurement happens, it is genuinely in both states simultaneously. Imagine flipping a coin. A classical bit is a coin that has already landed, heads or tails. A qubit is a coin that is still spinning. While it spins, it is simultaneously both. And here is where the power of quantum computation comes from. If you have 10 qubits all in superposition, the system is simultaneously exploring all 1024 possible combinations of zeros and ones. If you have 300 qubits, the system can simultaneously represent more states than there are atoms in the observable universe. The parallelism is exponential, and it comes directly from the physics of quantum mechanics. But superposition is only half the story. The other crucial feature is entanglement. When two qubits become entangled, their quantum states become linked in a way that has no classical analog. Measuring one qubit instantly determines something about the other, regardless of how far apart they are. Einstein found this so troubling that he called it spooky action at a distance, and spent years trying to find an alternative explanation. He could not. The experiments have been done. Entanglement is real. Particles that interacted in the past share a deep quantum connection that transcends the usual notion of spatial separation. In a quantum computer, entanglement allows qubits to coordinate their processing in ways that are impossible for classical bits. Information is not just stored locally, it is distributed and shared across the entire entangled system. This makes quantum computers extraordinarily efficient at solving certain classes of problems, particularly those involving simulation of quantum systems, optimization over large spaces, and cryptographic computations. Now here is the key insight. Nature does not use classical bits. Nature uses qubits. At the microscopic level, everything is quantum. Particles have superpositions. Systems entangle spontaneously. Quantum interference shapes the outcomes of physical processes. When physicists built the first quantum computers, they were not building machines that simulate quantum mechanics. They were building machines that run on quantum mechanics directly. They are the same kind of system. And that similarity is not just an interesting analogy. It suggests something deeper. The universe has quantum structure at every level. Its fundamental constituents obey quantum rules. Information is processed through superposition and entanglement. Events unfold through the resolution of quantum probabilities. These are not features that merely resemble quantum computation. These are the defining features of quantum computation, which is why the question physicists are increasingly asking is not whether the universe resembles a quantum computer. It is whether there is any meaningful difference at all. The most striking physical evidence for this perspective comes from the most extreme environments in the universe. black holes. And from a problem so difficult it remained unsolved for nearly 5 decades after it was first identified. In 1974, Stephen Hawking made a discovery that should not have been possible. Using a combination of quantum mechanics and general relativity, he showed that black holes are not perfectly black. They slowly radiate energy, a faint glow now called Hawking radiation, caused by quantum effects at the edge of the event horizon. This was a spectacular result, instantly recognized as one of the most important theoretical insights of the 20th century. But it came with a catastrophic implication. Hawking radiation is, by all appearances, purely thermal. It carries no information about what fell into the black hole. It does not matter whether you dropped in a book, a diamond, or an entire star, the radiation that comes out looks identical. Just a featureless thermal glow at a temperature determined only by the mass of the black hole. And as the black hole slowly evaporates, radiating away over billions upon billions of years, it eventually disappears entirely. That means the information it swallowed is gone. Not just inaccessible, not just scrambled, destroyed. And that is a catastrophe. Because quantum mechanics is built on the principle that information cannot be destroyed. Every quantum process is reversible in principle. The past can always be reconstructed from the present. If black holes violate this principle, if they genuinely erase information, then quantum mechanics is not a fundamental theory. It breaks down. And everything built on it, which includes essentially all of modern physics, becomes unreliable. This became known as the black hole information paradox. For decades, it sat at the center of theoretical physics like a splinter no one could remove. Hawking himself initially maintained that information was genuinely lost, and that quantum mechanics simply had to accommodate this fact. Other physicists, including Gerard 't Hooft and Leonard Susskind, argued fiercely that this could not be true. The disagreement became one of the great intellectual confrontations in the history of physics. The resolution, when it slowly began to emerge through decades of careful work, came from an unexpected direction. The language of quantum information and quantum computation. The growing consensus is that black holes do not destroy information. They scramble it. A black hole acts like the most efficient quantum information processor in nature, taking the information of everything that falls in, distributing it non-locally across the event horizon, encrypting it in the Hawking radiation in a form that is theoretically recoverable but practically impossible to decode. The information is not lost. It is preserved in a form so thoroughly scrambled that no observer could practically read it. But it is there. This view was supported in 2007 when Patrick Hayden and John Preskill showed that the late-stage Hawking radiation from an old black hole could in principle carry out the information that went in, just encoded in subtle quantum correlations too complex to decode without the full quantum state of all the radiation emitted across the black hole's entire lifetime. Their paper described this as the black hole as a mirror, a perfect but scrambled reflection of everything it consumed. Black holes in this picture are not the universe's garbage disposals. They are its most powerful quantum processors. They take structured, organized information and scramble it beyond recognition, but they do not break the fundamental rules of quantum mechanics. They push those rules to their absolute limit, but they obey them. And the very fact that physicists can only resolve the information paradox by treating black holes as quantum computers is itself evidence that the universe operates on quantum computational principles. The connection does not stop there. Around the same time physicists were unraveling the information paradox, a different set of researchers was making a related discovery. One that suggested not just that black holes process information, but that space itself might be built from it. The holographic principle emerged from the work of Jacob Bekenstein and later Stephen Hawking in the 1970s. When they calculated the entropy of a black hole, the measure of its information content, they found something bizarre. The entropy of a black hole is not proportional to its volume, as you might expect. It is proportional to the area of its event horizon. The surface area, not the volume. This seems like a technical detail, but it has enormous implications. If the information content of a three-dimensional region of space is described by its two-dimensional boundary, that means 3 dimensions might not be fundamental. Three-dimensional space might be a projection of information encoded on a lower dimensional surface. This is what physicists call the holographic principle. The idea that a lower dimensional description carries all the information needed to reconstruct a higher dimensional reality. Gerard 't Hooft formalized this idea in the 1990s, and Leonard Susskind extended it into what is now a major pillar of theoretical physics. But the most concrete realization came through a framework developed by Juan Maldacena in 1997, called the anti-de Sitter space conformal field theory correspondence, or by its shorthand, ADS-CFT. What Maldacena showed was a precise mathematical duality between two completely different theories. On one side, a theory of quantum gravity in a three-dimensional space with a specific geometry. On the other side, a quantum field theory with no gravity at all, living on the two-dimensional boundary of that space. Despite being completely different theories describing apparently different things, they are mathematically equivalent. Every calculation you can do in one has a precise translation in the other. They describe the same physics from two different perspectives. This is one of the most important results in theoretical physics of the last 30 years. And one of its deep implications is that space and gravity can emerge from a lower dimensional quantum system with no gravity. Space is not fundamental. It can be constructed from quantum information. The geometry of space, the curvature produced by gravity, the distance between 2 points. All of these can be derived from the entanglement structure of a quantum system that does not even contain space as a primitive ingredient. This was made more precise through the work of Shinsei Ryu and Tadashi Takayanagi, who in 2006 showed that the area of surfaces in the higher dimensional gravity theory corresponds directly to entanglement entropy in the boundary theory. Entanglement, the same quantum correlation that makes qubits coordinate in a quantum computer, is literally encoding the geometry of space. Mark van Ramsdonk developed this further with a remarkable thought experiment. If you take a quantum system on the boundary and reduce the entanglement between two regions, the corresponding regions in the bulk space physically pull apart. Reduce entanglement to zero, and those regions become completely disconnected. The spatial bridge between them breaks. This means entanglement is not just a feature of space. Entanglement is what holds space together. Space-time geometry, the arena in which everything we experience plays out, is stitched together from quantum correlations. In a universe built from quantum information, this is exactly what you would expect. A quantum computer does not just perform calculations within space. The connections it creates, the entanglement it generates between its components, are themselves building the structure that we would call space if we were looking at it from the inside. Another line of evidence comes from a seemingly unrelated area of quantum computing research: quantum error correction. When physicists build quantum computers, one of the central challenges is fragility. Qubits are extraordinarily sensitive to disturbances from their environment. Even tiny vibrations, stray electromagnetic fields, or thermal noise can disrupt a quantum state and introduce errors. To combat this, quantum computers use error-correcting codes. They spread the information from a single logical qubit across many physical qubits in such a way that errors affecting a small number of physical qubits can be detected and corrected without disturbing the logical information. In recent years, physicists working on ADS-CFT have discovered that the relationship between the bulk gravity theory and the boundary quantum theory has exactly the structure of a quantum error-correcting code. The information about what is happening deep inside the gravitational space is distributed redundantly across the boundary. Just like logical qubits are distributed redundantly across physical qubits in a quantum computer. This means that if part of the boundary is damaged or inaccessible, you can still recover the information about what happened deep inside. The bulk physics is protected against errors by the same mathematical machinery that quantum engineers use to make quantum computers reliable. Ahmed Almheri, Shidong, and Daniel Harlow made this precise in 2015, showing that the reconstruction of local bulk operators from boundary operators follows exactly the pattern expected from quantum error-correcting codes. The universe is not just performing computation. It is performing protected computation. It has error correction built in. Space-time geometry is not just an informational structure. It is a robust informational structure, resilient against the kinds of perturbations that would destroy more fragile systems. This suggests that the computational nature of reality is not incidental. It is engineered in the sense that the structure of physics is self-reinforcing, self-protecting, and extraordinarily stable. This connects to a question that has puzzled physicists for over a century. Why are the laws of physics so clean? Why is there conservation of energy, conservation of momentum, conservation of charge? Why do symmetries like rotational invariance and time reversal invariance hold so precisely? In the computational picture, these are not mysterious gifts of nature. They are stability conditions. They are the rules that must hold for the computation to remain consistent. A universe whose laws were not symmetric, whose conservation laws occasionally failed, would be a universe whose computation was noisy, unstable, and would rapidly degrade into incoherence. The laws we observe are the laws of a computation that has been running cleanly for 13.8 billion years. Their cleanliness is not a coincidence. It is a requirement for long-term computational stability. When physicists look at the double-slit experiment, one of the foundational experiments of quantum mechanics, they typically describe it in terms of wave-particle duality or quantum superposition. But there is another way to see it. When a single particle passes through two slits simultaneously and interferes with itself on the other side, the pattern of interference on the detector encodes information about both possible paths the particle could have taken. The detection event, the collapse of the quantum state, resolves this information into a specific outcome. This is quantum computation in its most elementary form. A physical process that takes multiple informational inputs, processes them through quantum interference, and produces a definite classical output. Every quantum mechanical experiment at its core has this structure. The laws of quantum mechanics are not simply descriptions of how particles behave. They are the operating rules of a computation. Superposition allows the system to hold multiple possibilities simultaneously. Entanglement allows those possibilities to be correlated non-locally. Interference allows certain possibilities to reinforce and others to cancel. Measurement resolves the computation into a definite output. These are not physical phenomena that happen to resemble computational operations. They are the primitive operations of quantum computation expressed in physical language. Now consider what this means for the nature of physical laws. The conventional picture is that the universe has laws and matter obeys them. The laws are given, external, absolute. But in the computational picture, something subtler is happening. The laws might be better understood as the self-consistent logic of a computation that has been running for a very long time. They are not imposed from outside. They are the rules that must hold for the computation to maintain its integrity. And this reframes a question that has puzzled scientists and philosophers for centuries. Why is there something rather than nothing? Why do these particular laws exist and not others? From a computational perspective, a complete answer may not be possible, but a partial answer emerges naturally. The laws that have persisted for 13.8 billion years are the laws compatible with stable, complex, long-running computation. Other configurations, other rule sets, might have collapsed into incoherence early, might have been computationally unstable, might have failed to maintain the conditions for complexity to emerge. The universe we inhabit is a computation that has been running long enough to produce atoms, stars, chemistry, biology, and minds. Its laws are not fine-tuned by external adjustment. They are the laws of a successful computation. This reframes the fine-tuning problem in physics. Physicists have long noted that the constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, the cosmological constant, appear to be tuned with extraordinary precision to permit the existence of complex structures, including life. Change any of them by even a small amount and the universe becomes sterile. This has seemed mysterious, even suspicious. Why should the constants be so convenient? In the computational picture, this has a natural answer. A universe whose constants do not permit stable information structures does not persist as a complex computation. It degrades quickly into uniformity or collapses. The reason we observe a universe with convenient constants is not that the constants were adjusted by some external agent, but that a universe with inconvenient constants does not produce observers to notice the inconvenience. The computation continues only where it can continue, and we are part of the computation that has continued. The connection between information and energy runs deeper than most people realize. In 1847, James Prescott Joule established the mechanical equivalent of heat, showing that work and heat are forms of the same thing. A century later, Claude Shannon established the mathematical theory of information, showing how to measure it precisely. And in 1961, Rolf Landauer showed that these two developments were related in a fundamental way. Landauer's principle states that erasing one bit of information must dissipate a minimum amount of energy into the environment. The minimum is small, roughly 2.8 times 10 to the minus 21 joules at room temperature, but it is real, measurable, and physically unavoidable. The reverse is also true. Creating information, setting a bit from an unknown state to a known one, requires energy. And reading information, performing a measurement, is itself a physical process that follows thermodynamic laws. Information is not abstract. It is thermodynamically physical. It has a minimum energy cost. It generates heat when erased. It participates in the second law of thermodynamics. In the language of statistical mechanics, entropy and information are the same quantity measured in different units. This means that when the universe increases in entropy, it is not just becoming more disordered in some abstract sense. It is processing more information, exploring more configurations of its quantum state space. The second law of thermodynamics is, in this view, a statement about the direction of computation. Systems evolve from states with fewer realized configurations to states with more. The universe moves from organized simplicity, a hot uniform plasma in the aftermath of the Big Bang, toward realized complexity, the rich tapestry of structures that gravity, chemistry, and quantum mechanics have woven over billions of years. The Big Bang, in this picture, was not simply the origin of matter and energy. It was the initialization event, the moment when the computation was set up with an extraordinarily low entropy, highly organized, information-rich starting state. The specific configuration of that initial state was not random. It was precisely structured, and the computation it launched has been running ever since, unfolding that initial structure into the elaborate complexity of the universe we inhabit. Roger Penrose has made this point with particular force. The entropy of the early universe was extraordinarily low, far lower than it needed to be for any particular arrangement of matter and energy. The initial conditions were special in a way that cannot be explained by ordinary physical processes operating before the Big Bang. In Penrose's view, this specialness is the deepest puzzle in cosmology. But in the computational framework, the question becomes, what kind of initialization produces a computation capable of running for 13.8 billion years and generating minds that can reflect on the computation itself? That framing brings us to one of the most profound implications of the quantum computer model of the universe, self-reference. A computation that generates structures capable of modeling the computation itself is, in a specific technical sense, a recursive computation. It loops back on itself. It contains within it representations of its own logic. We are one such representation. Human minds, and perhaps minds of other forms wherever they exist, are processes within the universal computation that have become capable of modeling that computation. We use mathematics, which is the language of information and logic, to describe physical laws, which are the operating rules of the computation. We build quantum computers, which are small instances of the same kind of computation the universe performs, in order to study the universe. We are the computation studying itself. Not metaphorically, structurally. This is not a mystical observation. It is a mathematical one. In computer science and logic, self-referential systems have been studied intensively since the work of Kurt Gödel and Alan Turing in the 1930s. Gödel showed that any sufficiently powerful logical system contains true statements that cannot be proved within the system. Turing showed that no sufficiently powerful computer can determine in advance whether an arbitrary program will halt or run forever. Both results arise from self-reference. A system that can model itself runs into fundamental limits when it tries to fully understand itself. These limits apply to the universe as a quantum computer. There are questions about the universe that the universe, through minds embedded within it, can never fully answer. Not because we are not clever enough, but because those questions ask the computation to fully simulate itself, which requires more resources than the computation has available. A perfect model of the universe would need to be as complex as the universe. It cannot fit inside the universe it is modeling without displacing the universe it is supposed to represent. This is not a technological limitation. It is a logical one. The Bekenstein bound makes this precise. Jacob Bekenstein showed that the maximum amount of information that can be stored in a given region of space is proportional to the surface area of that region, measured in units of the Planck area, which is a square with sides of about 1.6 times 10 to the minus 35 meters. This is an extraordinarily small unit of area, and the resulting information capacity is astronomically large for ordinary regions of space. But it is finite. Any region of space can contain only a finite amount of information. This means the universe itself, the observable universe, has a finite information capacity. Seth Lloyd estimated this at around 10 to the power of 120 bits. And it means that a perfect self-simulation of the observable universe would require 10 to the power of 120 bits of storage, which is exactly what the universe contains. The model would leave no room for anything else. Perfect self-knowledge is impossible. Understanding is always partial, always an approximation, always missing something about the system it describes. Science, in this framework, is the computation iterating on itself, building increasingly accurate but always incomplete models. But there is something remarkable in this limitation. The fact that we can identify the limit means we understand something deep. We know that knowledge is bounded not by our cleverness, but by the structure of the system we inhabit. We know that the rules we call physics are the logic of a computation that has been running since the first instant of time. We know that the space we move through is built from entanglement. We know that the black holes dotting the universe are the most powerful information processors in nature. We know that error correction, the key technology of quantum computing, is built into the very structure of spacetime. That is not nothing. That is extraordinary. 13.8 billion years into a computation, within a galaxy of 400 billion stars, on a planet orbiting a middle-aged star in an outer spiral arm, on a planet with 4.5 billion years of chemical and biological computation stored in the geological record and the genome, minds have emerged that can read the source code of the universe and begin to understand what it is doing. This brings us to the dark implication that the computational picture cannot escape. If the universe is a computation, it is subject to the laws of thermodynamics, and the second law has an inevitable conclusion. Entropy increases. Usable energy is gradually converted into heat, spread out, made unavailable for further work. Over timescales that are difficult even to write down, the universe will cool. Stars will exhaust their fuel and go dark. The last stellar embers will cool to black dwarfs over timescales of perhaps 10 to the power of 15 years. Black holes, the long-lived remnants of collapsed stars and galaxies, will slowly evaporate through Hawking radiation over timescales reaching 10 to the power of 100 years. And eventually, the universe will approach what physicists call heat death, a state of maximum entropy. Uniform temperature, no gradients, no structure, no computation. From the computational perspective, this is not just a physical description. It is the termination condition, when every usable energy gradient has been exhausted, when no further state changes can occur, the computation halts. The universe does not disappear. Its matter and radiation persist, but it stops doing anything. It freezes into an eternal, unchanging configuration. The program still exists on the hardware, but the hardware has no more power. This implies something about our current situation. We are not at the beginning of the computation, but we are not near its end either. We are in a rare and fleeting phase of extraordinary complexity and activity. Stars are burning. Galaxies are evolving. Chemistry is active. Biology is running. Minds are computing. The rate of information processing in the universe right now is incomparably higher than it will be in 100 billion years, which will itself be incomparably higher than in 100 trillion years. We exist at a local maximum of computational richness, and that richness is not permanent. The universe is drifting toward a quieter state with every passing second. The entropy is rising. The usable energy is diminishing. The complexity, though it may persist and grow locally for billions of years to come, is operating on borrowed time at the cosmological scale. Eventually, the gradients that drive everything, including thought and life, and the curiosity that leads physicists to ask these questions, will dissipate. The signal will fade into noise, but quantum mechanics adds one more strange chapter to this story. Information, even in the heat-death state, is not destroyed. The principle of unitarity still holds. The quantum state of the universe, even a cold, dark, maximally entropic universe, is still a specific quantum state. All the information from every event that ever happened, every particle interaction, every thought, every collision, every quantum measurement performed since the beginning of time, is encoded, in principle, in the quantum state of whatever the universe becomes. Not accessible, not readable, not usable, but there. This is a strange kind of immortality. Nothing is forgotten by the universe, even though nothing can be recovered. The information exists in the same sense that numbers exist, perfectly precise, eternally valid, but with no system capable of reading them. The universe's memory is perfect. Its amnesia is total. Some physicists have speculated about what happens after the heat death, given infinite time. The physicist Ludwig Boltzmann introduced a concept, now called the Boltzmann brain problem, that highlights the bizarre implications of thermodynamic fluctuations over infinite timescales. Even in a universe at maximum entropy, quantum fluctuations can locally decrease entropy for brief moments. Given infinite time, any configuration of matter, no matter how improbable, will eventually occur by chance. This includes configurations that constitute functioning observers, minds that briefly coalesce from the thermal noise, experience something, and then dissolve back into it. These are called Boltzmann brains. The concept is more troubling than it first appears. If the universe is infinite in time, and Boltzmann brains occur with some finite probability per unit time in any sufficiently large region, then Boltzmann brains are far more numerous than evolved observers like us. And if most observers are Boltzmann brains, then any given observer should expect to be one. But Boltzmann brains would have chaotic, self-inconsistent memories. They would not expect to find themselves in a coherent, orderly universe with a consistent past. The fact that we do find ourselves in such a universe is evidence against the idea that we are Boltzmann brains, which in turn constrains theories about the long-term future of the universe and its computational trajectory. There is also the more dramatic possibility that the universe's computation does not merely slow down and halt, but resets. Physicists have identified what is called the vacuum stability problem. The universe's quantum fields sit in a specific configuration, a specific energy state called the vacuum. But calculations suggest that this vacuum state might not be the lowest possible energy state. There might be a lower energy state, a true vacuum, that the universe could in principle quantum tunnel into. If this happened, a bubble of true vacuum would form and expand at the speed of light, carrying new physical laws, different constants, different rules. Everything it encountered would be restructured into the new mode of existence. This possibility, called vacuum decay, would not destroy information in the quantum mechanical sense. But it would transform the rules of the computation so radically that the information currently encoded in particles, fields, and structures would be reorganized into an entirely alien form. For all practical purposes, it would be a reboot. The old computation would end. A new one, with different rules, would begin. If this has happened before, if there was a previous computational epoch with different physical laws that quantum decayed into our universe, then the Big Bang itself might be understood as such a transition. Not a creation from nothing, but a phase change in an ongoing computation. Not an initialization, but a reinitialization. This is speculative, but it is not idle speculation. It is the kind of question that follows naturally once you accept the computational framework and ask it honestly. What does all of this mean for the future of physics? The quantum computer model of the universe is not a finished theory. It is a framework, a perspective, a set of ideas that are converging from multiple directions. Quantum information theory, quantum gravity, the physics of black holes, the structure of spacetime thermodynamics, and the foundations of quantum mechanics are all pointing toward the same underlying picture. Reality at its deepest level is information being processed according to quantum rules. The next steps are not easy. The central unsolved problem in theoretical physics is the unification of quantum mechanics and general relativity. Quantum mechanics describes the behavior of the very small with extraordinary precision. General relativity describes the behavior of the very large, of spacetime itself, with equally extraordinary precision. But the two theories are mathematically incompatible. They cannot both be correct in every situation. At extreme scales, near the Planck length where space and time begin to lose their classical meaning, both theories fail. The hope is that the quantum computational framework points toward the resolution. If spacetime emerges from entanglement, as the holographic approaches suggest, then the quantum theory is more fundamental than the gravitational theory. Gravity is not a force that exists alongside quantum mechanics. It is a consequence of quantum information dynamics. Finding the precise mathematical version of this statement is one of the great open problems of modern physics. A related challenge is explaining the emergence of the classical world from quantum foundations. We experience a classical reality. Objects have definite positions. Cats are either alive or dead, not in superposition. Decisions have outcomes. But quantum mechanics describes a world of superpositions and entanglement. The process by which quantum probabilities become classical facts, called decoherence and measurement, is understood at a technical level, but remains philosophically contested. In the computational picture, this process is the output stage of the computation, the moment when quantum calculation resolves into classical information. Understanding it better would illuminate not just physics, but the nature of experience itself. There is also the question of consciousness. It is mentioned here not as mysticism but as a scientific question. Minds are information processing systems. They receive inputs, process them through quantum and classical operations in the brain, and produce outputs that shape behavior and memory. In a universe built from information, minds are not exceptional. They are one class of information processing structure among many. But they are unusual in one specific way. They are structures within the computation that model the computation. They are self-referential processes. And self-reference in information theory is not trivial. It is the source of both the richest structures and the deepest limits. Whether consciousness requires something beyond quantum information processing, or whether it is fully explained by it, is a question physicists, neuroscientists, and philosophers are beginning to ask in mathematical terms rather than purely metaphysical ones. Quantum computers themselves will be a crucial tool in exploring these questions. As quantum hardware advances, researchers will be able to simulate increasingly complex quantum systems with increasing fidelity. Small black hole analogs have already been simulated in quantum devices. Aspects of holography have been reproduced in the lab. As these simulations grow more sophisticated, they will provide direct experimental windows into the informational structure of spacetime. The goal is not to build a simulation of the entire universe, which is impossible for the reasons already discussed. The goal is to identify the key structures, the computational primitives, the error-correcting codes, the entanglement geometries that underlie physical reality, and to study them directly. This is reverse engineering at the deepest level, using quantum computers, which are instances of the same kind of computation as the universe, to decode the logic that runs everything. We are in the early stages of this project. The theory of quantum gravity is incomplete. The connection between quantum information and space-time geometry is understood in specific mathematical models, but not yet in full generality. The role of quantum error correction in the structure of reality is suggestive, but not proven in detail. There are many pieces of the puzzle still missing, but consider how far we have come. 50 years ago, information theory and physics were largely separate disciplines. Physicists studied particles and fields. Information theorists studied bits and channels. The connection was not obvious, not to most people. Today, the language of information and computation has become central to our best understanding of quantum gravity, of the nature of spacetime, of the behavior of black holes, and of the foundations of quantum mechanics. This is not a temporary fashion. It is a genuine shift in how physicists understand the structure of reality, and the shift has implications beyond physics. If the universe is fundamentally a computation, then the distinction between natural and artificial computation is not as sharp as it seems. Human-built computers are not imitations of nature. They are instances of the same kind of process that nature has always performed. When we build a quantum computer, we are not creating something foreign to the universe. We are taking a small piece of the universe's own computational machinery and directing it toward problems we find interesting. That means there is a sense in which computation, in the broadest sense, is not something humans invented. It is something humans discovered. We found it already running, everywhere, at every scale, in every particle interaction and quantum measurement. We learned to harness it, and we are only beginning to understand how deep it goes. The universe began 13.8 billion years ago in a state of extraordinary order, extraordinary low entropy, and extraordinary informational richness. Since that moment, it has been computing continuously, processing its initial state through quantum operations, generating structure and complexity, evolving toward higher entropy states while creating, along the way, stars and planets and chemistry and life. And on at least one planet, it has generated structures capable of asking what kind of process created them. That question, and the fact that it can be asked at all, is part of the computation. The curiosity is part of the system. The physics we write down is the universe describing its own rules to itself. Every experiment we run is a small instance of the universe measuring itself. Every quantum computer we build is a tiny mirror reflecting the logic of the whole back at us in concentrated form. We do not yet know how deep the informational structure of reality goes. We do not know whether there is a substrate beneath quantum mechanics, a level more fundamental than qubits and entanglement, or whether quantum information is the bottom of the stack. We do not know what, if anything, preceded the computational initialization we call the Big Bang, or whether that question has a meaningful answer from within the system. We do not know how spacetime and quantum gravity are unified at the Planck scale, or precisely how the geometry of space emerges from entanglement patterns. These are not failures. They are frontiers, and they are being actively explored by physicists, mathematicians, and quantum computer scientists whose tools are growing more powerful with each passing year. The answers, when they come, will not be simple. They will not fit easily into ordinary language. They will require mathematics, and probably new mathematics to express. But they will be answers about the most fundamental thing there is: the nature of reality at the deepest level, accessible to a mind operating within reality. For now, what we can say is this: the universe is not just a place where things happen. It is a process that takes information and transforms it according to quantum rules, generating at each step a world more complex and more intricate than the one before. We are part of that process, not observers of it from outside, not passengers in a machine we did not build, but active components in the computation, built from the same logic that builds stars, woven from the same entanglement that weaves spacetime, and endowed with the improbable capacity to trace the logic of the whole back to its source. If that does not change how you see the world, consider it once more. Every particle that makes up your body is in a quantum state right now. Every interaction between those particles is an act of information processing. The neurons firing as you read this sentence are performing quantum and classical computations simultaneously. Your thoughts, your memories, your sense of being present in this moment are information patterns embedded in the same universal process that has been running since the beginning of time. You are not watching the universe compute. You are the universe computing. And the fact that this piece of the computation can ask what the computation is, can wonder about its own nature, can work backward from the output to reconstruct the logic of the process, is perhaps the most remarkable thing the universe has done with its 13.8 billion years. What comes next is not something we can predict because the computation is irreducible. There is no shortcut. You have to let it run, but the direction is clear. More information, more structure, more self-knowledge, until the gradients are gone and the processing quiets. Between now and that distant silence, there is an extraordinary amount of computation left to perform. And some of the most important questions it will process are the ones you are already asking. If you find yourself thinking differently about what exists, if the boundary between physics and information seems less clear than it did before, that is not confusion. That is the computation advancing. And if that makes you want to follow this further, to watch these ideas develop as the science deepens, then stay close to the work. The best results are still ahead. Let us go deeper into something that the outline of the quantum computer model only hints at: the texture of space itself. When you stand in an open field and look at the sky, space appears perfectly smooth, continuous, infinite in all directions, a seamless medium through which things move. This intuition is so built into our experience that questioning it feels almost absurd. But physicists have been questioning it seriously since the early 20th century, and what they have found is deeply unsettling. Planck length, named after Max Planck, the physicist who first introduced the quantum of action and inadvertently launched quantum mechanics. The Planck length is approximately 1.6 times 10 to the minus 35 meters. To grasp how small this is, consider that a proton has a diameter of roughly 1 femtometer, which is 10 to the minus 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. If you tried to draw a proton on a sheet of paper and wanted the Planck length to be visible at the same scale, the proton would need to be larger than the entire observable universe. At this scale, the combined predictions of quantum mechanics and general relativity break down. Quantum mechanics says that the uncertainty in the position of any object is inversely proportional to the precision with which you know its momentum. Push the precision of position measurement down to the Planck length, and the energy required to make that measurement becomes so large that you create a black hole. You cannot measure anything smaller than the Planck length without the act of measurement destroying the thing you are trying to measure. Space below the Planck length is not just inaccessible. It may not exist in any meaningful sense. Carlo Rovelli and Lee Smolin, working on a theory called loop quantum gravity, took this seriously and proposed that space is literally granular at the Planck scale. Not approximately granular in the way sand appears smooth from a distance, but is made of particles up close. Genuinely, irreducibly granular. Space, in this picture, is made of fundamental units of volume called spin foams, and their interactions define the geometry of space at the smallest scales. Space is not a smooth continuum that physics plays out within. It is a network of discrete quantum interconnections whose collective behavior we experience as smooth geometry at the scales we can observe. If this is correct, then space is itself a quantum system. It has a quantum state. It undergoes quantum evolution. It can be in superposition and can be entangled. And computation, in this view, is not something that happens within space. It is the process by which space evolves. The universe is not a stage on which a computation is performed. The stage is the computation. This perspective connects naturally to something called spin network dynamics, the mathematical framework at the heart of loop quantum gravity. A spin network is a graph, a collection of nodes connected by edges, where each edge carries a quantum number representing the area of the surface it crosses, and each node represents a quantum of volume. The entire three-dimensional geometry of space at a given moment is encoded in the structure of this graph. Space is not filled with spin networks. Space is the spin network. Time in this picture is not a smooth river flowing from past to future. It is a sequence of discrete transitions between spin network configurations. Each transition is like a clock tick, a step in the computation. Between ticks, nothing happens because there is no between. The universe evolves one quantum step at a time, updating its configuration according to quantum rules. And the result, viewed at scales far above the Planck scale, looks like smooth space and time evolving continuously according to the equations of general relativity. This is exactly the relationship between a discrete digital computation and its continuous-looking output. When you watch a video on a screen, the image appears continuous. Colors blend smoothly, motion flows without visible steps. But underneath, the video is a sequence of discrete frames, each made of discrete pixels, each pixel encoded by discrete binary numbers, all processed by a digital system that operates in discrete clock cycles. The continuity is an emergent property of the discrete underlying process. In the same way, the smooth spacetime of our experience may be the emergent property of the discrete quantum evolution of spin networks at the Planck scale. The computational metaphor becomes almost irresistible here. A digital video has a resolution, a specific number of pixels, and a specific frame rate. Below those scales, the video has no information. Similarly, loop quantum gravity suggests that spacetime has a resolution, the Planck length and the Planck time. Below those scales, space and time have no information. There is no position smaller than the Planck length. There is no duration shorter than the Planck time, which is approximately 5 times 10 to the minus 44 seconds. These are not just limits of measurement. They are limits of existence. The Planck time, about 5 times 10 to the minus 44 seconds, is the time it takes light to cross a Planck length. It is the minimum meaningful time interval in a universe governed by quantum gravity. 1 Planck time is 1 tick of the universe's fundamental clock, and in 13.8 billion years, the number of Planck times that have elapsed is approximately 8 times 10 to the 60 power. That is the number of computational steps the universe has taken from its initialization to the present moment, 8 followed by 60 zeros. Each step involving the update of a quantum configuration of staggering complexity. Each step, the universe computing the next frame of its own evolution. Now let us examine how this discrete computational structure connects to something you encounter in everyday physics: the maximum speed limit of the universe. The speed of light, approximately 299,792,458 meters per second in vacuum, is not just the speed of light. It is the maximum speed at which any information can propagate through space. Nothing carrying information can travel faster. This is not a contingent engineering limitation, like the speed limit on a highway. It is a fundamental structural fact about the universe. In the computational picture, this makes perfect sense. The speed of light is the update speed of the computation. It is the maximum rate at which a change in one region of the computation can propagate to affect a neighboring region. If space is a network of quantum nodes, and each node can only update its state when it receives a signal from adjacent nodes, then the speed of light is the signal propagation speed across the network. Information can travel no faster because the computation updates no faster. The speed of light is the clock rate of the universe's computational substrate. This means that causality, the rule that causes must precede their effects, is a direct consequence of the computational structure of spacetime. A cause at one location cannot affect a distant location faster than light because it takes that much time for the update to propagate through the computational network from one node to the next. Causality is not a rule imposed on the computation from outside. It is an intrinsic property of how the computation propagates updates through its structure. Entanglement, however, seems to violate this. When two entangled particles are separated and one is measured, the quantum state of the other changes instantaneously, regardless of distance. This has been demonstrated experimentally, most famously in experiments by Alain Aspect in 1982 and in increasingly precise refinements by many research groups since. The correlation appears instantly, without any signal propagating through space. How can this be consistent with the speed of light as the maximum information speed? The resolution is subtle and important. Entanglement does not transmit information. When you measure one entangled particle, you learn something about the other one instantly. But you cannot control what outcome your measurement will produce, and therefore you cannot use entanglement to send a message faster than light. The correlation is real, but it cannot be exploited to communicate. The correlations are hidden in the quantum state until measurement reveals them, but the revelation does not allow faster than light signaling. In computational terms, entanglement represents a non-local correlation in the computational state that was established when the particles interacted in the past. The computation does not send a signal from one particle to the other when a measurement is made. Rather, the state of both particles is jointly specified by the entangled quantum state, and a measurement on one reveals information that was already encoded in that joint state. No update propagates. The correlation is already there, embedded in the structure of the computation. This is actually one of the features that makes quantum computation so powerful. Entanglement allows quantum systems to be correlated in ways that have no classical analog, and those correlations can be exploited to perform certain computations much more efficiently than any classical approach. The universe uses this feature constantly. Every quantum interaction generates entanglement. The universe's computational state is a web of entanglements of staggering complexity, connecting particles that interacted in the past, maintaining correlations across space, encoding history in the structure of quantum correlations that span every scale from subatomic to cosmic. In a very real sense, the universe remembers every interaction that has ever occurred, not in any accessible way, not in any way that allows a practical retrieval of past events. But the quantum state of the universe, which evolves unitarily according to the Schrödinger equation and its relativistic extensions, in principle, encodes the complete history of every interaction since the beginning of time. The universe's memory is written in entanglement. An entanglement once created does not simply disappear. It spreads. It propagates. It gets incorporated into the broader quantum state of the system. Old entanglements are not destroyed. They are submerged, becoming part of the vast background of correlations that make up the universe's total informational structure. This has a striking implication for the arrow of time. Why does time have a direction? Why do we remember the past but not the future? Why do broken eggs not spontaneously reassemble? The microscopic laws of physics are time-symmetric. If you reverse the direction of time, every individual particle interaction would still obey the same laws. Yet the macroscopic world has a clear temporal direction. Entropy increases. Structure decays. Time flows forward. The computational picture offers a precise answer. The universe began in a state of extremely low entropy, extremely low information content in the thermodynamic sense. As the computation has proceeded, entropy has increased, not because the laws of physics prefer high entropy, but because there are vastly more high entropy states than low entropy ones. Starting from a specific low entropy state, the computational evolution almost inevitably leads toward higher entropy, simply because most of the available states have higher entropy. The direction of time is the direction in which the computation evolves from a specific, improbable starting configuration toward the generic, probable high-entropy configurations that occupy the vast majority of state space. Memory itself is a computational process. When you remember the past, you are accessing a stored informational state in your brain that was created by past sensory inputs. Future events have not yet created such stored states, which is why you cannot remember the future. But in a deeper sense, the universe also accumulates a kind of memory. Each quantum interaction creates entanglement. Each entanglement is a record encoded in the quantum state of the interaction that created it. The universe's past is not lost. It is encoded in the present quantum state, scrambled beyond practical recovery, but present in principle. The computational framework also sheds light on one of the deepest puzzles in quantum mechanics, the measurement problem. When you perform a quantum measurement, a system that was in a superposition of multiple possibilities resolves into a single definite outcome. The mathematics of quantum mechanics describes this through the collapse of the wave function. But the equation that governs quantum evolution, the Schrödinger equation, never produces collapse. It evolves quantum states smoothly and continuously, always maintaining superposition. So where does the collapse come from? This question has been debated since the 1920s when quantum mechanics was first formulated. Niels Bohr argued that the collapse was a fundamental feature of reality, the moment when the quantum world made contact with the classical world. Einstein hated this answer and spent years trying to show that quantum mechanics was incomplete. Hugh Everett in 1957 proposed the many worlds interpretation, in which collapse never actually happens. Instead, all possible outcomes occur, with the universe branching into different versions at each measurement. Decoherence developed into a detailed theory by Dieter Zeh, Wojciech Zurek, and others from the 1970s onward offered a more physically precise account of how classical behavior emerges from quantum foundations without requiring explicit collapse. In the computational picture, these approaches converge on a consistent story. When a quantum system interacts with a macroscopic measurement apparatus, it becomes entangled with that apparatus. The apparatus in turn interacts with its environment, spreading the entanglement across billions of particles. This rapid spreading of entanglement into the environment is what decoherence describes. Once entanglement has spread into a large number of environmental degrees of freedom, the interference terms that would reveal the quantum superposition become effectively inaccessible. The system appears to have collapsed into a definite state, not because anything nonlinear has occurred, but because the quantum information encoding the superposition has been irreversibly scrambled into the environment. This is quantum error correction working in reverse. Instead of protecting quantum information from the environment, decoherence spreads quantum information into the environment so thoroughly that it cannot be recovered. The quantum coherence of a superposition is a computational resource. Decoherence is the process by which that resource is consumed and degraded into classical information. And what looks to us like the collapse of the wave function is simply the boundary between the quantum phase of the computation, where superpositions are intact and exploitable, and the classical output phase, where the result has been registered, and the quantum coherence has been irreversibly distributed into the environment. This means that every measurement in the universe, every interaction between a quantum system and a macroscopic detector, is a computation completing and delivering its output. The result is classical, definite, and irreversible, not because the quantum rules have broken down, but because the quantum information has been distributed so widely that recovering it would require access to more resources than are available. The universe is constantly performing quantum computations and outputting classical results. And we, as macroscopic observers, only ever see the classical outputs. The quantum processes underlying them are hidden in the entanglement structure of the environment. There is another implication worth exploring. If the universe is a quantum computer, then its evolution is, in principle, reversible. Quantum mechanics is time-symmetric. The Schrödinger equation can be run backward just as well as forward. In a closed quantum system with no decoherence, you could in principle reverse all the operations and recover the initial state perfectly. But the universe is not a collection of isolated systems. It is a single, globally entangled quantum state, and its evolution entangles systems with each other so rapidly and thoroughly that reversal is impossible in practice. This practical irreversibility is what gives rise to the arrow of time, the second law of thermodynamics, and the asymmetry between past and future that we experience. The quantum computation is time reversible in principle, but the specific path it has taken, from the low entropy initialization of the Big Bang to the complex present state, is extraordinarily improbable in reverse. The probability of the universe spontaneously computing backward from the present state to the past is not zero, but it is so infinitesimally small that for all practical purposes, time flows in one direction only. Physicists call this the past hypothesis, the assumption that the universe began in a state of extremely low entropy. This assumption is required to explain the arrow of time within the framework of statistical mechanics, and it is confirmed by every cosmological observation. The universe began highly ordered, highly structured, informationally rich in a specific sense, and it has been evolving toward less organized configurations ever since. Not because disorder is preferred, but because disordered configurations are overwhelmingly more numerous in the universe's state space. Now let us turn to something that often generates confusion: the relationship between quantum computation and the simulation hypothesis. The simulation hypothesis, popularized in philosophical form by Nick Bostrom in 2003, proposes that sufficiently advanced civilizations would likely create simulations of minds or entire universes, and that if such simulations are possible, most minds would find themselves in simulations rather than in base reality. Therefore, the hypothesis suggests we are likely simulated. The quantum computer model of the universe is often confused with this idea, but they are categorically different. The simulation hypothesis posits an external computing system, running on hardware that is more fundamental than the simulated reality, producing the appearance of a universe for the benefit of simulated observers. The quantum computer model makes no such claim. It does not posit an external system. It does not require a simulator. It says the universe itself is the computation, not simulated by a computer. The universe simply is a computational process, in the same way that a river is a fluid dynamical process. The river is not simulating fluid dynamics. It is fluid dynamics. The universe is not simulating quantum computation. It is quantum computation. This distinction matters enormously. The simulation hypothesis imports all the questions about base reality. If we are simulated, what is the hardware running the simulation? Who built it? What are the rules of that deeper reality? The questions multiply and become unanswerable. The quantum computational picture is self-contained. The universe follows quantum rules. Those rules generate everything we observe. There is no deeper substrate that needs explaining because the quantum rules are themselves the substrate. They are the bottom of the stack. Or are they? This is one of the genuinely open questions. We do not know whether quantum mechanics is fundamental, or whether it is itself an emergent description of something more primitive. There are research programs, like those exploring pre-quantum mechanics from cellular automata proposed by Gerard T. Hooft, that attempt to derive quantum mechanics from even more fundamental classical or discrete dynamics. If such an approach succeeded, it would suggest that quantum computation is itself an emergent phenomenon from a deeper level of description. The universe would still be a computer, but the computer's hardware would be more primitive than qubits. Most physicists consider these approaches unlikely to succeed without sacrificing important features of quantum mechanics, particularly its experimental success in describing nature. But the question of whether quantum information is truly fundamental, or whether there is a substrate beneath it, is legitimately open. It is one of the deepest questions in physics, and answering it would be a revolution, comparable to the discovery of quantum mechanics itself. What is not in serious doubt is that quantum informational concepts have become essential tools for understanding the most fundamental aspects of physical reality. This happened gradually, over decades, as physicists working in seemingly unrelated areas kept encountering the same mathematical structures. Black hole entropy connected to information. Holography connected spacetime geometry to boundary information. Entanglement connected to spatial structure. Error correction connected to gravitational physics. The convergence was not planned. It emerged from following the mathematics honestly wherever it led. This kind of convergence is rare in physics and is usually a sign that something deep is being uncovered. When the same mathematical structure appears in multiple independent contexts, it typically means you have found a feature of reality itself, not just a feature of one particular model. The appearance of quantum information theory across all of these different areas of physics strongly suggests that information is genuinely fundamental to the structure of reality and is not just a useful calculational tool. The mathematician John von Neumann, who made crucial contributions to both quantum mechanics and the theory of computation, understood this connection earlier than most. Von Neumann entropy, named after him, is the quantum mechanical generalization of Shannon information entropy. In classical information theory, Shannon entropy measures the uncertainty in a probability distribution. In quantum mechanics, von Neumann entropy measures the information content, or equivalently, the degree of entanglement of a quantum state. The mathematical formulas are analogous. The concepts are deeply connected. Von Neumann also developed the mathematical framework of operator algebras that underlies modern quantum mechanics. And he independently developed the concept of a self-replicating automaton, a mathematical machine that can copy itself, which later inspired ideas about cellular automata and the computational structure of physical laws. He saw computation and quantum physics as connected at a fundamental level, and subsequent decades have borne out that intuition more thoroughly than even he might have expected. Alan Turing, working in the 1930s and 40s, laid the foundations of the theory of computation independently of quantum mechanics. Turing's universal machine, a mathematical description of a general-purpose computer, showed that any well-defined computation could in principle be performed by a single machine, given enough time and memory. This result was about abstract mathematics, not physics. But Turing was also aware that real computation required physical implementation, and he understood that the limits of computation were connected to the limits of physical systems. Decades later, Richard Feynman brought these threads together explicitly. In a celebrated talk in 1981, Feynman argued that simulating quantum systems with classical computers is exponentially hard. The state space of a quantum system with many particles grows exponentially with the number of particles, making classical simulation intractable for any system of practical size. Feynman's conclusion was that to efficiently simulate quantum systems, you need a quantum computer, a machine that itself operates according to quantum rules. He was proposing quantum computing as a tool for physics simulation, but his argument had a deeper implication that he highlighted. The universe, which is a quantum system, naturally performs the computation of its own evolution. It does this efficiently because it is quantum. A classical computer trying to simulate the universe would need exponentially more resources than the universe itself. But a quantum computer the same size as the universe could simulate the universe exactly and trivially because it would just be the universe. The universe is its own most efficient simulator because it is the computation itself. David Deutsch, working in the 1980s, formalized this into the theory of quantum computation and proposed the first concrete model of a universal quantum computer. Deutsch was explicitly motivated by physical considerations. He wanted to know what computations could be performed by any physical system obeying the laws of physics. His conclusion was that quantum mechanics allows a class of computations that classical mechanics does not, and that a universal quantum computer could simulate any physical process exactly. This was not just a technical result. It was a statement about the relationship between physics and computation at a fundamental level. The Church-Turing-Deutsch principle, named after Alonzo Church, Alan Turing, and David Deutsch, proposes that any physically realizable computation can be performed by a universal quantum computer. This is the quantum mechanical extension of the classical Church-Turing thesis, which proposed that any computable function can be computed by a Turing machine. The quantum extension says that the class of computations performable by a quantum computer is exactly the class of computations performable by any physical system whatsoever, as determined by the laws of quantum mechanics. Quantum computation is the most general form of physical computation there is. If the Church-Turing-Deutsch principle is correct, and most physicists and computer scientists who have considered it carefully believe it is, then the following is implied. Any physical process is a quantum computation. Any system evolving according to the laws of quantum mechanics is performing a quantum computation. The burning of a star is a quantum computation. The formation of a protein is a quantum computation. The firing of a neuron is a quantum computation. And the universe as a whole, evolving from its initial quantum state through 13.8 billion years of quantum dynamics, is the largest and most complex quantum computation that we know of. This is why the question of whether the universe is a quantum computer has such a definitive-sounding answer. Not because physicists have proven it in the way you prove a theorem, but because the quantum mechanical structure of reality and the mathematical theory of quantum computation are built from the same foundations. They are not two different things that happen to resemble each other.
They are the same thing described in two different languages. Let us examine one more area where this convergence has become scientifically productive: the study of complexity.
Not complexity in the everyday sense of being complicated, but complexity in the precise sense developed in computational theory and applied to physics. In computational complexity theory, problems are classified by how the resources needed to solve them, time and memory, scale with the size of the problem. Some problems are easy. They can be solved with resources that grow only polynomially with problem size. Others are hard. The resources required grow exponentially, making large instances practically unsolvable. The complexity class called NP, which stands for non-deterministic polynomial time, contains problems whose solutions are easy to verify but potentially hard to find. The most famous open question in mathematics, whether the complexity classes P and NP are equal, asks whether every problem whose solution is easy to verify is also easy to find. The overwhelming expectation among computer scientists is that they are not equal, that some problems are genuinely hard to solve, even though solutions can be quickly checked. But the question has not been proven. What does this have to do with physics? It turns out that many fundamental physical questions are NP hard or harder. Finding the ground state energy of a general quantum system is NP hard. Simulating quantum circuits beyond a certain depth takes exponential time on a classical computer. Computing properties of strongly interacting quantum systems is computationally intractable in general. Physics and computation share the same landscape of difficulty. Moreover, physicists have begun asking whether complexity plays a fundamental role in the structure of spacetime itself. In the context of ADS-CFT, some researchers have proposed that the size of the Einstein-Rosen bridge, the interior of a black hole, is proportional not just to the entropy of the boundary system, but to its computational complexity. This is the complexity equals volume conjecture, proposed by Leonard Susskind. The idea is that the computational complexity of the quantum state on the boundary, a measure of how many quantum operations are required to prepare that state from a simple reference state, corresponds to the volume of the wormhole in the bulk. This would mean that computational complexity is not just an abstract property of algorithms. It is a geometric property of spacetime. The complexity of a quantum state is literally reflected in the geometry of space, in the volume and structure of regions connected by quantum entanglement. Complexity, entropy, geometry, and computation are not four different things. They are four different ways of measuring the same underlying informational structure of reality. Susskind has gone further, proposing a principle he calls complexity equals action, in which the rate of change of complexity in the boundary system equals the action of the bulk system evaluated over the Einstein-Rosen bridge. Action, in physics, is one of the most fundamental quantities, from which the equations of motion of physical systems can be derived through the principle of least action. Connecting it to computational complexity is a remarkable step, suggesting that the fundamental dynamic principle of physics is itself a statement about the rate of information processing. If these conjectures are correct, then the universe is not just computing. It is computing in such a way that the geometry of its spacetime literally encodes the complexity of its computational state. To understand the geometry of the universe is to understand the complexity of its quantum computation. And to understand the complexity of its quantum computation is to understand the geometry of the universe. Space and computation are not just analogous, they may be identical, two perspectives on the same structure. These ideas are still being developed. The conjectures are not proven. The exact mathematical relationship between complexity and space-time geometry is still being worked out. But the convergence of these ideas, coming from black hole physics, quantum information theory, computational complexity theory, and quantum gravity, suggests that the physics community is approaching a synthesis of profound depth, the kind of synthesis that happens rarely in the history of science and that reshapes the entire conceptual landscape when it arrives. What would such a synthesis look like? It would be a complete theory of quantum gravity, built on the foundations of quantum information. It would explain spacetime geometry as an emergent property of quantum entanglement and computational complexity. It would resolve the black hole information paradox completely. It would unify quantum mechanics and general relativity into a single coherent framework. It would explain why the universe began in a low entropy state. It would give us the precise sense in which the universe is a quantum computer, including the rules of the computation, the structure of the state space, and the relationship between computational complexity and physical geometry. We do not have this theory yet. Building it is the work of a generation, perhaps more, but the pieces are being assembled. The holographic principle adds CFT correspondence, quantum error correction in spacetime, the complexity volume and complexity action conjectures, the emergence of spacetime from entanglement. These are all pieces of the same puzzle, and the puzzle, when completed, will tell us what the universe fundamentally is. Not in the sense of a metaphor or a useful analogy. In the sense of a precise, experimentally testable, mathematically rigorous theory of the deepest structure of reality. A theory that says, here are the qubits, here are the gates, here is the error correction code, here is the algorithm, and here is how the geometry of space and time emerges from the computation of this algorithm on this quantum state. That theory will not make the universe seem less mysterious. It will make it seem more so because precision reveals depth. The more exactly you can describe something, the more you realize how extraordinary it is that it exists at all. A universe that is a quantum computer is not a universe explained and domesticated. It is a universe whose computational nature is suddenly visible in all its staggering complexity, running every second with a computational power that makes everything humanity has ever built look like a single bit. And somewhere in the middle of all that computation, briefly, on a pale blue dot orbiting an unremarkable star, particles arrange themselves into structures that could wonder about the process they were part of. That wonder is itself a computation. This sentence is a computation. The thoughts forming in your mind as you absorb these ideas are computations. Every moment of awareness is a small eddy in the universal computation, a brief self-referential loop in which the system becomes aware of itself. How long this particular eddy persists, whether it grows or shrinks, whether minds like ours learn enough about the computation to meaningfully participate in shaping its output, these are questions not of physics but of choice. The universe will compute regardless. The only question is what kind of computation we choose to perform within it. The research continues. Quantum computers are being scaled up, their error rates reduced, their qubit counts increased. String theory and loop quantum gravity are being developed further, searching for the complete theory of quantum gravity. The holographic principle is being extended and tested in new contexts. Researchers at the intersection of quantum information and quantum gravity are publishing results that would have been inconceivable a generation ago. The pace is accelerating, and every result, every experimental test, Every theoretical insight moves us slightly closer to the answer to the most fundamental question we have ever asked. What is the universe? Not what is in the universe, but what is it? At the level below atoms and fields and space-time, below every substrate we have so far identified. What is reality made of at the most fundamental level that the universe will allow us to see? The answer, as best as we can tell right now, is information. Quantum information, processed according to the rules of quantum mechanics. Encoded in entanglement, protected by quantum error correction, reflected in the geometry of space, bounded by the Bekenstein limit. Evolving from a low-entropy initialization toward a high-entropy heat death, along a path of staggering complexity, through 13.8 billion years of continuous computation. That is the universe we inhabit. Not a void, not a machine, not a simulation, a computation. The most ancient, the most powerful, and the most complex computation in existence. And we are part of it, not incidentally, not as observers, but as the computation's most recent and strangest output. Structures that compute and wonder about their own computing. The universe began. It has been running since. It will continue long after every star is dark. And in this brief window, in this extraordinary phase where complexity is at its richest, in this moment where the computation is most active and most intricate, we have the chance to understand what is happening. Not fully, not finally, but partially, imperfectly, and with growing precision. That is science. That is the computation studying itself. And that might be the most remarkable thing the universe has ever done with its time. There is one more thread that deserves careful attention, because it sits at the intersection of all the ideas we have explored and points toward the future of both physics and technology. It is the question of what happens when the computation builds computers of its own. For most of the universe's history, computation has been performed by natural systems following natural rules. Stars performing nuclear fusion are computing the lowest energy configurations of protons and neutrons. Crystals forming from molten rock are computing the minimum energy arrangements of atoms in a lattice. DNA replicating is computing a copy of an informational sequence. Neurons firing are computing representations of sensory information and directing behavioral responses. All of this is computation in the technical sense, information processing according to fixed rules. But roughly 4 billion years ago, on at least one planet, the universal computation produced something new. Organisms capable of heritable variation and natural selection. This introduced a new kind of computation into the universe. Evolutionary computation, a process that searches over the space of possible organismal designs by generating variation and selecting for reproductive success. Evolution is not an algorithm designed by anyone. It is an algorithm that arose spontaneously when the right conditions were in place. Replicating molecules with occasional copying errors in an environment that exerted selective pressure. Evolution is extraordinarily powerful as a search algorithm. Over 4 billion years on Earth, it has produced organisms of staggering complexity and capability. Eyes that detect single photons. Brains with 100 billion neurons making 100 trillion connections. Immune systems that learn to recognize novel pathogens within days. Echolocation systems in bats that can resolve features at millimeter scale. The diversity and ingenuity of biological solutions to ecological problems is a testament to the power of evolutionary computation applied over geological timescales. But evolution has limits. It is slow. It can only explore the space of possible organisms through random mutation, which is a blind walk through a vast and complex landscape. It cannot plan. It cannot look ahead. It cannot deliberately engineer solutions. It discovers, but it does not design. Roughly 300,000 years ago, a different kind of computation emerged on Earth. Directed cognition. Human minds capable of modeling the world, predicting consequences, planning sequences of actions, and deliberately solving problems. This introduced intentional search into the universe's computational repertoire. Instead of blindly walking through the space of possibilities, human cognition can analyze the structure of a problem and deliberately navigate toward solutions. The result, over the past few thousand years of civilization and the past few centuries of science, has been an explosion of discovered knowledge and engineered technology without precedent in the history of life on Earth. Humans have learned to harness fire, agriculture, metallurgy, writing, mathematics, the printing press, steam engines, electricity, radio, computers, nuclear energy, genetic engineering, and now quantum computing. Each of these technologies represents a qualitative expansion in the universe's local computational capabilities. Quantum computing is the most recent and perhaps the most fundamental of these expansions. Previous technologies amplified human physical capabilities: stronger muscles, faster movement, longer range communication. Computing technology amplified human cognitive capabilities: faster calculation, larger memory, more complex problem solving. Quantum computing goes one step further. It amplifies the universe's own native computational mode, allowing us to harness the quantum mechanical processes that underlie all of physical reality. When a quantum computer runs a quantum algorithm, it is not imitating quantum mechanics. It is performing quantum mechanics, deliberately, under controlled conditions, directed toward specific computational goals. It is the universe's quantum computational substrate being harnessed by the products of that same computational substrate, minds that arose from quantum chemistry and evolutionary computation, to deliberately perform quantum computations of our choosing. This is recursive in a way that has few parallels. The universal computation has produced, through 4 billion years of evolution and 300,000 years of directed cognition, a species of organisms that can deliberately harness the computational substrate of the universe itself. We are quantum systems using quantum systems to compute about quantum systems. The loop is genuinely closed. Current quantum computers are crude instruments. The largest have a few thousand physical qubits. The error rates are high, limiting the depth of useful circuits. The range of problems they can solve better than classical computers is still narrow, though growing rapidly. But the trajectory is clear. Error rates are falling. Qubit counts are rising. New algorithms are being developed that demonstrate quantum advantage in practically important domains. Within the next decade, quantum computers with millions of physical qubits and practical error correction are expected by many researchers in the field. Such machines would be capable of simulating quantum chemical reactions with enough precision to design new materials and drugs. They would be capable of solving certain optimization problems of commercial significance, and they would be capable of simulating quantum field theories and aspects of quantum gravity with unprecedented fidelity. The last capability is the most scientifically profound. Using quantum computers to simulate quantum gravity means using the universe's quantum computation to explore what quantum gravity looks like. We would be constructing small, controlled instances of the same kind of information processing that occurred in the earliest moments of the universe, when quantum gravity was the dominant physics, and the distinction between space and time had not yet solidified into the familiar structure we inhabit today. These simulations will not reproduce the early universe. They will not be large enough, or complex enough, or operate under the right conditions to do that. But they will allow physicists to test ideas about quantum gravity in situations where the results can be directly computed and compared with theoretical predictions. They will serve as laboratories for exploring the informational structure of spacetime in controlled settings. They will be windows into a regime of physics that we have so far only been able to approach through mathematics. The first such windows are already open. Experiments by the team led by Maria Spirapoulou at Caltech and the group at Google Quantum AI in 2022 used a 9-qubit quantum processor to simulate a wormhole. Not a real wormhole in physical space, but a quantum system whose informational dynamics mirror the mathematical description of a wormhole in the context of ADAS-CFT. Information was transmitted through this quantum simulation in a way that mimics the behavior of information traversing an Einstein-Rosen bridge in the theoretical framework. The result was controversial, with some physicists arguing that the simulation was too small to demonstrate anything genuinely new about quantum gravity, and others arguing that it represented an important proof of concept. The debate reflects the genuine difficulty of bridging the gap between quantum computation in the lab and quantum gravity in the universe. But the direction of travel is clear. Quantum computers are becoming tools for probing the informational structure of spacetime, and the experimental results will accumulate. Alongside these technological developments, the theoretical understanding continues to deepen. Physicists are developing new mathematical frameworks for understanding the relationship between quantum information and quantum gravity. The field called quantum information and quantum gravity, sometimes abbreviated as QI/QG, has grown from a niche interest into one of the most active areas of theoretical physics. Conferences, journals, research programs, and graduate fellowships are dedicated to it. A generation of physicists is being trained at the intersection of these fields. The mathematical tools being developed include new approaches to quantum error correction, new methods for calculating entanglement entropy in quantum field theories, new frameworks for understanding the emergence of spacetime from quantum information, and new connections between computational complexity theory and physical phenomena. Each of these tools represents a refinement of our ability to understand the informational structure of reality. One particularly promising development is the growing understanding of how chaos and complexity interact in quantum systems. Quantum chaos, the study of how quantum systems exhibit chaotic behavior analogous to classical chaos, has been connected to questions about how quickly information is scrambled in quantum systems. Fast scramblers, systems that distribute information across all their degrees of freedom as quickly as possible, have been identified as the most efficient possible quantum information processors. And black holes have been proposed as the fastest scramblers in nature, saturating a bound on the rate of information scrambling that can be derived from fundamental physical principles. This bound, sometimes called the Maldacena-Schenker-Stanford bound on chaos, states that the rate of quantum chaos cannot exceed 2 times pi times the temperature of the system divided by a fundamental constant called the reduced Planck constant. Black holes saturate this bound. They are maximally chaotic. They scramble information at the fastest rate that the laws of physics permit. And they do so because of their quantum gravitational nature, the combination of quantum mechanics and strong gravity that makes black holes unique among physical systems. This connects back to the deeper picture. Black holes are not just gravitational sinks. They are the universe's most extreme and efficient quantum computational systems. They take structured information, scramble it with maximum efficiency, and release it in Hawking radiation in a form so thoroughly encoded that recovering the original information is computationally harder than any problem we know of. They are the universe's most powerful quantum hash functions, converting input information into output radiation, with maximal irreversibility from a practical standpoint and maximum information preservation from a fundamental standpoint. The fact that the laws of physics constrain the rate of information scrambling, and that this rate is saturated by black holes, tells us something deep about the universe as a computation. The universal computation has a maximum processing rate per degree of freedom. This rate is set by the same fundamental constants that appear in quantum mechanics and thermodynamics. The computation cannot go faster than this rate, and the most extreme physical systems, black holes, operate precisely at this limit. Everything else in the universe operates below this rate. Chemical reactions are slower. Biological processes are slower. Electronic computers are vastly slower. Quantum computers in the lab are currently much slower than the theoretical maximum. But the maximum rate is there, set by physics, applicable to any quantum system, and saturated only by the most extreme objects in the universe. This rate can be expressed as roughly 112 bits per second per unit of energy in joules. At room temperature, this corresponds to a maximum processing rate of about 40 trillion bits per second per kilogram of matter. This is the ultimate computing speed, the maximum rate at which any physical system can process information. A human brain at rest, performing its approximately 10 to the power of 14 synaptic operations per second, is running far below this rate. Current quantum computers are far below it. Even the most powerful computing systems we can imagine building are far below it. But the universe itself is not below it. Each black hole, each quantum system near its maximum entropy, each region of space operating at the limits imposed by thermodynamics, is computing at or near the universal maximum rate. The universe as a whole, summing the contributions of all its quantum degrees of freedom, is operating at the maximum computational power possible under the laws of physics. It is not wasting any computational capacity. It is using all of it. This is perhaps the most visceral way to appreciate the claim that the universe is a quantum computer. It is not just that the universe resembles a quantum computer or behaves like one. It is that the universe is saturating the physical bounds on computation. It is using every quantum degree of freedom available to it, at the maximum rate permitted by its temperature and energy, to process information. There is no more efficient computation imaginable. The universe is not just a quantum computer. It is the optimal quantum computer, running at maximum efficiency, constrained only by the thermodynamic limits that are themselves expressions of the computational rules it follows, and we are part of this optimization. Our bodies, our brains, our civilizations, our machines, all operate within these limits and contribute to the universal computation. Our quantum computers, when we build them, are not external additions to the universe's computation. They are deliberate reorganizations of the universe's existing computational capacity, directed toward specific ends by minds that are themselves outputs of that computation. The story is circular in the best possible way. The universe computes. The computation produces complexity. Complexity produces minds. Minds study the computation. Studying the computation reveals that minds are the computation studying itself. And this revelation produces more questions, more experiments, more understanding, more computation. The loop is not vicious. It is generative. Every iteration deepens the understanding. Every question answered opens 10 more. Every quantum computer we build gives us new tools to probe the quantum computation we inhabit. Where does it end? In the very long run, with heat death, with the gradual exhaustion of usable energy gradients, and the slowing of the computation to a halt. But that end is so far in the future, measured in timescales that make the current age of the universe look infinitesimally brief, that it functions more as a boundary condition than as a practical constraint. Between now and then, the computation continues, increasingly self-aware, increasingly complex, increasingly capable of understanding its own nature. We are in the early stages of this self-understanding. The universe has been computing for 13.8 billion years and has only recently, in the last few thousand years of recorded science, developed the capacity to understand the rules of its own computation. We are at the beginning of this understanding, not near the end. The physics we have developed so far is extraordinary in its power and precision, but it is incomplete. The theory of quantum gravity remains unfinished. The relationship between quantum information and spacetime geometry is only partially understood. The ultimate nature of the quantum computational substrate is unknown, but we are making progress. Each generation of physicists, working with more powerful tools, better mathematics, and richer experimental data, moves the understanding forward. The quantum computer model of the universe is not a final answer. It is a framework that is proving extraordinarily productive, generating new results, new connections, new experiments, and new questions. It is the direction in which the science is pointing. And following that direction is the work of the coming decades. The universe began with a single initialization, a quantum state of extraordinary low entropy and extraordinary information richness. It has been computing ever since, exploring the consequences of that initial condition, generating every structure and every event that has ever occurred. And within that computation, briefly and improbably, structures have emerged that can ask what the computation is. We are those structures. And the question is open. Consider what it would mean to fully accept this picture, not as a hypothesis, but as a working reality. Every experiment you perform is a query to the universal computation. Every measurement you make forces the computation to output a definite result. Every theory you write down is an attempt to reverse engineer the source code. Every quantum computer you build is a deliberate subcomputation nested within the larger one. This is not mysticism. It is engineering. Understanding the universe as a quantum computation opens practical doors. If spacetime geometry is encoded in entanglement, then manipulating entanglement in laboratory quantum systems can teach us about the geometry of spacetime at the Planck scale. If black holes are the universe's most efficient information processors, then studying the physics of black holes gives us access to the ultimate limits of computation. If the laws of physics are the operating rules of a quantum computation, then finding those laws more precisely means understanding the computation more deeply and being able to predict its future outputs with greater accuracy. The practical implications extend beyond pure physics. The same informational perspective that illuminates quantum gravity also transforms how we think about materials science, chemistry, biology, and computation. Quantum computers will simulate quantum chemistry with precision impossible for classical systems. New materials with exotic quantum properties will be designed computationally. Drug molecules will be modeled at the quantum level. The informational structure of biological systems, including the quantum coherent processes now known to play roles in photosynthesis, enzyme catalysis, and possibly neural computation, will be understood more deeply. The universe has given us the tools to understand it. Mathematics, logic, the scientific method, and now quantum computers, which operate on the same principles as the universe itself. Using these tools to understand what the universe is at its deepest level is not just an abstract intellectual pursuit. It is the computation folding back on itself. The universe using part of itself to understand the whole. What we learn in the next few decades of physics and quantum computing will reshape our picture of reality more profoundly than anything since the development of quantum mechanics a century ago. The convergence of quantum information theory and quantum gravity is pointing toward a synthesis that will change how we understand space, time, information, and existence itself. Stay with this work. The questions being asked now are the deepest questions ever posed. The answers, when they come, will be worth waiting for. And if you are someone who finds these questions as compelling as the physicists who spend their lives pursuing them, then you already know what to do. Follow the science, ask the questions, build the tools, run the computation. The universe will still be here. It has been for 13.8 billion years. It will continue for far longer still, and somewhere in the middle of all that time, in this brief phase where complexity peaks and minds exist to wonder about it, there is the chance to understand something real about what everything is. That chance is open right now. And that is why the work matters. One final perspective that ties every thread together. Throughout all of what has been discussed, there runs a single unifying theme that is easy to miss because it is everywhere. The relationship between structure and randomness. Pure randomness contains no information. A perfectly random sequence of bits has maximum entropy, but carries no meaning because it has no pattern. Any bit is equally likely, so knowing some bits tells you nothing about the others. Pure randomness is, in a deep sense, computationally inert. Nothing can be built from it because nothing can be predicted within it. Pure order, the opposite extreme, also contains very little useful information. A sequence of all zeros tells you everything about the sequence in a single bit. It is all zeros. There is no complexity here, no richness, no possibility of interesting structure. Pure order is also computationally inert in a different way. It has already reached its final state. Complexity, and by extension computation, lives in the narrow band between pure randomness and pure order. This is the regime where patterns exist but are not trivially predictable, where structure is present but not exhaustively described by a simple rule. This is where crystals form and snowflakes grow and proteins fold and ecosystems evolve and weather systems develop and galaxies spiral and minds arise. The rich middle ground between perfect order and perfect chaos is where the universal computation operates. The physicist Murray Gell-Mann, who won the Nobel Prize in Physics in 1969 for his contributions to the theory of elementary particles, developed this idea into a formal framework called effective complexity. Effective complexity is a measure of the length of the shortest description of the regularities of a system, distinct from the irregularities which are left to chance. A perfectly regular crystal has low effective complexity because its regularities are simple. A perfectly random gas also has low effective complexity because there are no regularities worth describing. A living organism has high effective complexity because its regularities, the genetic code, the protein folding rules, the metabolic pathways, the neural architecture, are extensive and non-trivial. The universe in its current state has extraordinarily high effective complexity. Its regularities, the laws of physics, are simple and elegant. But the patterns those laws have generated over 13.8 billion years of computation are of staggering richness and variety. The laws are simple. The output is complex. This is exactly the signature of a powerful computation. Simple rules generating enormous complexity over sufficient time. And the universe's trajectory has been from lower effective complexity toward higher effective complexity. In the very early universe, there were only the simplest structures: protons, neutrons, electrons, photons, and the simplest atoms, hydrogen and helium. As the computation proceeded, stars formed, cooked heavier elements in their cores, exploded, scattered those elements, formed second-generation stars with planets, allowed chemistry to proceed, produced molecules of increasing complexity, and ultimately produced life, which is the most complex information processing system we know of, culminating in minds that can measure and describe their own complexity. This trajectory toward higher effective complexity is not in conflict with the second law of thermodynamics. Entropy is increasing, but entropy and effective complexity are not the same. Entropy measures the total number of possible microscopic states consistent with a macroscopic description. Effective complexity measures the regularity of structure. It is possible for both to increase simultaneously. For the universe to become more disordered at the microscopic level, while producing more elaborate structure at intermediate scales where chemistry and biology operate. The universe is threading a needle. It is increasing its entropy, as it must, while simultaneously generating, in local pockets against the entropic tide, structures of increasing complexity. Life and mind are the most dramatic examples of this local complexity generation, powered by the flow of energy from concentrated sources like stars through chemical systems that use that energy to build and maintain structure. We are not exceptions to thermodynamics. We are expressions of it. We exist because the universe is flowing from low entropy to high entropy, and because some of that flow can be captured and redirected into the building of complex structures. Our existence is not an accident in an indifferent universe. It is a predictable outcome of the universal computation in a universe that begins with low entropy, has physics that permits complex chemistry, and has enough time for evolution to discover the most complex information processing architectures thermodynamics allows. This might be the most important insight the quantum computational picture offers. Not that the universe is cold and mechanical. Not that we are mere programs in a cosmic computer, but that the richness of reality, the existence of chemistry and biology and mind, is exactly what you would expect from a quantum computation of sufficient power, running from a low entropy initial state for sufficient time. We are not surprising. We are inevitable, not in the sense that we were planned, but in the sense that the universal computation reliably generates structures of increasing complexity when the conditions permit. And the conditions in our universe do permit. That is perhaps the most grounding conclusion of all. The universe is not hostile to complexity. It generates complexity. It has been generating it for 13.8 billion years and will continue to generate it for billions more. We are part of that generation, the current leading edge of a process that has been building toward greater complexity since the first moments of time. The quantum computer does not stop. The computation continues, and we, as part of it, have the extraordinary privilege of being complex enough to know that we are part of it. To trace the logic back to its foundations, to ask what the computation is, and to begin, slowly, imperfectly, but genuinely, to understand the answer. That understanding is the universe knowing itself. And that, in the end, might be what 13.8 billion years of computation has been building toward.